In this video, I'm going to start covering the Fundamental Theorem of Calculus. This is a two-parter. In the middle, there is a big honking proof. I'll let you know in the notes where it is so you don't have to look at it. You won't have to reproduce it on a test, but those who are going to be math majors might want to look at it just to get a feel for what real mathematics is like. So we start by defining a function g of x to be the integral from a to x of f of t dt. And here's just a generic graph of f of t. So g of x represents the area from a to x, this pink area. So let's look at an example. G of x is, that a should have been a 0, sorry about that. So I want the integral from 0 to x of f of t dt. Here's f of t. So g of 1, let's start with g of 0. G of 0 will be 0 because there ain't no area from 0 to 0. There's just nothing there. G of 1, well, I'm going to have this area, which is 1, the area of this triangle, which is also 1. So g of 1 is 2. Now, when I look for g of 2, I'm going to still have the 2 from before because I want all the area between 0 and 2. So I'm going to have all that area plus 3 more. So I get a 5. Then I'll do g of 3. I have the original 5. And then I have the area of this mess, which is, that's a half. That's 5 halves. Oh, I already did 5 halves. 5 halves. So 1, 2, 3, 4, 5 halves. So I get 15 halves. And if I integrate to 4, I have what I had before, plus 2 more for 19 halves. Some of you may recognize this from the problems from class on Thursday last week. A lot of you got to it, but not everybody did. Let's look at another one. If we are integrating, remember that if it's above the graph, it's positive. If it's below the graph, it's negative. Okay. And again, this should have been a 0. That's what I get for cutting and pasting. So again, g of 0 is 0. Ain't nothing there. G of 1, well, this area is 1. If I go from 0 to 2, my area is 2. Now, if I go from 0 to 3, this area here in this section is 1, but when I integrate it, it's a negative 1. So g of 3 is going to be what I had before, 2, minus the area here, which is minus 1, so I get a 1. And the next step, I'm going to subtract the area that's in this chunk here, and that's negative 2. So I had 1 before, I subtract 2, g of 4 is negative 1. So, before I prove this, I want you to recall from calculus the extreme value theorem. If f is continuous on an interval ab, then there exists a c and d in a and b such that f of c is less than f of x is less than f of d for all x, that upside down a means for all x in the interval ab. That just means that f of x has a maximum and it's got a minimum somewhere in the interval. The fundamental theorem of calculus says that if f is continuous on the interval ab and g of x is defined by g of x is from the integral from a to x of f of t dt, then g of x is an antiderivative of f. In other words, f prime of x is f of x for all the x between a and b, basically wherever f of x is defined. So let's do a proof of this. So the derivative of a function is just regurgitating the definition here. H goes to 0, x plus h minus g of x all over h. Now what exactly is g of x plus h minus g of x? Well, that's the integral from a to x plus h of f of t dt minus the integral from a to x of f of t dt. All that was divided by h, so I just pulled it out in front to get it out of my hair. Now, if this is going from a to x plus h, and this is going from a to x, the only thing that's left is that stuff in the middle, x to x plus h. So let's take a look at this here. I have some, between x and x plus h, I have some d that hits the maximum, that is the maximum, and at some c where f of c is the minimum. So let's see what we have here. This is my d. This yellow rectangle, you can't really see it because it's kind of light over here. This yellow rectangle represents the area if I used f of d as the height. And down here, the green represents the rectangle if I use f of c as the height. So the actual height has to be the pink stuff, has to be somewhere between the green and the yellow. So let's write that in math. f of ch, that is the size of the green rectangle. is less than or equal to the area under the curve from x to x plus h, and that's less than h times f of d, which is the area of the yellow triangle. Sorry, rectangle. Other problem gone. I can then say, well, the integral from x to x plus h of f of t is just that g of x plus h minus g of x is between these two. And now I'm going to divide everything by h. I get something that looks a little bit more familiar. So I have f of c is less than or equal to the difference quotient, which is less than or equal to f of d. What can I do with that? Well, let's look at f of c. F of c, as h goes to 0, f of c is just going to be heading toward x, because there's no place for it to hide. It's got to be in the middle of x to x plus h. If there's no h, it's at x. Same thing over here, f of d. As h goes to 0, my d is going to get closer and closer to whatever that x is. So the limit as d goes to x of f of d is f of x. Well, if the low side is going to f of x and the high side is going to f of x, the middle gets squished in the middle. Yes, called the squeeze theorem. So the limit as goes to 0 of the difference quotient must also be f of x. That's your proof, because that's the derivative. Ta-da! So the theorem is, I'm not going to read all this. Yes, I am. The fundamental theorem of calculus says that if f is continuous on an interval and g of x is defined by g of x is equal to the integral from a to x of f of t, then g of x is an antiderivative of f. In other words, g prime is equal to f of x. For all a less than or equal to x less than or, sorry, not or equal to, all x between a and b. Now, notice, all I care about a, really, is that it's a number. It's a number where f of t is defined. So if I've got a function that's defined on the entire interval, on the entire real plane, real line, I can let a equal 0, I can let a equal negative 50, I can let a be anything. So anything in this form where I have a number here and an x up here, the derivative is going to be just f of x. What is that? What is f of x? So I just rewrite this f of t, but with the x wherever the t's are. Let's look at this. So let's say I have g of x equals the integral from 0 to x of arctan of t dt. And I'm going to take the derivative of that. And the derivative is arctan of x. All I have to do is take this arctan and replace the t with an x. As long as I'm going from a number to x. That's important. Now, here's another one. Here I'm going from a number to -1. Oh no, Megan, it's -1. I don't give a shit. So we're going from a number to x squared. Okay, we're not actually going up to x. We went to x squared. So we have to do a chain rule. So if I take the derivative, I'm still going to put the top thing in for here, but then I need to multiply by the derivative of what I stuck in. So in other words, I have the x squared goes here where the t was, but I need to multiply by the derivative because of the chain rule. So that's one thing I can do. Another thing is, what if there are no numbers? Great. What if I go from 2x to 5x? What the hell is that? Well, let's rewrite that. We can rewrite that. What's your favorite number? Mine's 0. I'm going to rewrite that as 2x to 0 of this stuff plus 0 to 3x. Okay, we're getting closer. I have a number to something. I'm cool with this part, but this has the function to 0 to a number, not a number to 0. So I need to flip that. And as you may recall from class, or maybe not, if you flip the integrands, if you flip the limits of integration, it becomes negative, because it's like the base is now a negative length instead of a positive length, if you think about it that way. So I can rewrite that as negative the integral from 0 to 2x of sine of t cubed minus 2 dt. Blah. Now I can take the derivative. I will get this first one becomes negative. I stick in for t cubed. I stick my 2x cubed minus 2. And then I have to multiply by the derivative of what I stuck in, which is 2. The second part, I'm going to stick in 3x for my t, and then subtract 2, multiply by the derivative of what I stuck in, and I get a 3. I can clean it up a little bit, but not much. That's the derivative. So that's what we're going to do in this section, is take the derivative and talk about areas and all that kind of good stuff. Hope you enjoy that. Have a great day.